Welcome. We're going to get started with our empirical rule video today. And first, we use the empirical rule when we have the graph of a normal distribution. And a normal distribution always has a bell shape to it. So in this spot below, we can see a normal distribution. It has the bell shape. And there's two important things about this normal distribution. The center of our curve starts at mu, which is the same as the mean. We use mu to represent mean in statistics. And then we can see different markings, kind of tally marks going out, and that represents standard deviations. So the lines here from 68 in the red, that's one standard deviation below the mean and one standard deviation above the mean. And the empirical rule tells us that about 68% of data fall between that one standard deviation below and one standard deviation above the mean. The empirical rule also tells us that between two standard deviations, two standard deviations above and two standard deviations below, that would be the black lines, that 95% of our data falls in there. And then lastly, 99.7% of all values fall within plus or minus 3 standard deviations. That would be the blue or purple lines here. We can further use that information, the 68, 95, 99.7, to kind of break those percentages down into smaller intervals. So here is what happens when we break down those percentages. So instead of seeing 68 between -1 and +1, we can see them broken in half. 34, 34, and then going out, we can 13.5 on either side, 2.35, and 0.15 after the -3 and +3 standard deviations. We're going to use this to help us answer some questions. So the first question we're going to answer is what percent of values between the mean and two standard deviations above. So here's the mean, here's two standard deviations above. To find what percent of values are between there, all we need to do is add up those two percentage chunks. So 34 plus 13.5%, and when we do that, we get a final answer of 47.5%. Next question, what percent are between -3 standard deviations and the mean? So this time we're looking between the mean and -3 standard deviations. So we're just going to add up the 34, 13.5, and the 2.35, those three chunks that fall between the mean and -3 standard deviations. And we get an answer of 49.85%. One more. What percent of values are between -2 standard deviations and +1 standard deviations? So we can see from our picture we need to add up the 13.5, 34, and 34%, which is what we did. And the answer is 81.5%. Okay. The try now says what percent of values are between -1 standard deviations and +3 standard deviations. You can pause the video now and try this on your own. Okay, so now if you did this on your own, you should add up 34 plus 34 plus 13.5% plus 2.35% and get 83.85%. Awesome. Okay, so often we're not necessarily just given that curve and asked to answer questions like that. Usually we're asked to answer a word problem, kind of a question in context. So here's an example of a question like that. This question says, an example of an early application of statistics was in the year 1817. A study of chest circumferences among a group of Scottish men exhibited an approximately normal distribution. Their chest circumferences range from 33 to 48 inches, with a mean chest measurement of 40 inches and a standard deviation of 2 inches. Use the empirical rule, which we also often call the 68, 95, 99.7 rule, to help you understand the distribution of chest circumferences in the study. So the first thing we want to do when we're doing a problem like this is to draw a normal curve and label it. So here I've drawn my normal curve, and I've put in my percentages from my other picture, but I have also put in the values that were given to me in the problem. So I know the mean is in the middle, that was 40 inches. I know that the standard deviation is 2 inches, so 1 standard deviation above the mean is 2 plus 40, the mean. So 42, I go up another 2, another standard deviation to get to 2 standard deviations away, and so on. And then below the mean, I subtract 2 to go down a standard deviation each time. Once I've drawn this picture, the problems are relatively easy to solve, using the same method as the last problem. So question 1 says, about what percent of men in the population had a chest measurement between 38 and 42? So here's 38, here's 42. Well, 34 plus 34, I would add those two segments up, and I can see that 68% of men had chest measurements in that range. Next question, about what percent of men in the population had chest measurements between 36 and 42? So 36, 42, I would need to add up 13.5 plus 34 plus 34, which I did down here. And my final answer, if I can get this little sticky bit off, is 81.5, which I also wrote here, which has another sticky bit that's going to be hard to get off. There we go, 81.5. Okay, here's another one. About what percent of the men in the population had chest measurements between 36 and 46? So here's 36, here's 46. I would need to add up 13.5, 34, 34, 13.5, and 2.35, which I did and got 97.35, which is also what's right here. Okay, this one is going in reverse. This one says about 95% of men in the population had chest measurements between what? Well, we can go back to our empirical rule, which is right here. 95% of all values fall within 2 standard deviations. So 2 standard deviations below my mean is 36. 2 standard deviations above my mean is 44. So they would fall between 36 inches and 44 inches, which I will show you in just a second. There we go. So between 36 and 40 inches, between those 2 standard deviations above and below. Okay, here we go. What would you expect the biggest chest measurement to be for the 0.15% of men with the smallest chest measurements in the population? So smallest chest measurements are down here, and we want to know kind of what's the highest chest measurement you could have to be in the bottom 0.15%. So here's the bottom 0.15%, and we see that this boundary here is at 34 inches. So that is the largest chest measurement you could have and still be in the bottom 0.14% for chest measurements. So 34 inches is our answer there. This one says, what would you expect the smallest chest measurement to be for the 2.5% of men with the largest chest measurements in the population? So if we look on our graph, we do not see 2.5%. But if we do a little addition, we can easily figure out that 2.35 plus 0.15, that equals 2.5% altogether. So that tells me that that the boundary for the top 2.5% is right here at 2 standard deviations, or 44 inches, which we see right here. Okay. Last page. This is a try now, so I'll give you a second to pause and try each of the problems. Okay. So assuming you've done the problem and you've paused and you're ready to go, here I labeled my mean in the center, which was 35, and I marked my standard deviations, 3 standard deviations above the mean and 3 standard deviations below. We know 68% of our data is within 1 standard deviation below and above the mean, so that would be between 30 and 40. And so that's what I wrote, between 30 and 40. 95% of our data is within 2 standard deviations. That would be 35 is the middle, go down 2 to 25, go up 2 to 45, so between 25 and 45. This one, what percentage of the population or data is above 40? So here's 40, I want to know above, so I would need to add in those 3 chunks, which I could either pull and look at the graph from above. I could look at from my notes earlier and find those percentages, which was 13.5 here between 40 and 45, 2.35 between 45 and 50, and then 0.15 after 50, and we would get 16%. Or we also could know that the mean splits the data exactly in half. So 50% of our data is on this side, and we know that from 35 to 40, 34% of our data lives there. So the rest has to be enough to add up to 50, while 50 minus 34 gets us the 16% as well. So there are often multiple ways to come to the same answer, and it doesn't really matter which way you use, as long as it works. Okay, last example real quick. This one says the times required for a group of students to complete the physical fitness obstacle course result in a normal curve, and the mean time is 21 minutes, and the standard deviation is 4. So here, I've marked my graph with percents, and I've also labeled the mean in the middle and added and subtracted standard deviations. The first question, what percent took longer than 29 minutes? Here's 29 minutes, so I would add up those 2%, which I did, and I get 2.5%. Okay. Next one, what percent took less than 29 minutes? Well, I could add up all of those percents and get an answer, but I know that the whole normal curve adds up to 100%. And I know that the part above 29 adds up to 2.5%. So I can just do 100 minus 2.5 and get the correct final answer of 97.5%. Next question. What percent took between 13 and 29 minutes? I would just add up 13.5 plus 34 plus 34 plus 13.5, which is 95%. I also could have remembered the empirical rule and noticed that 13 was 2 standard deviations below my mean, and 29 was 2 standard deviations above. And I know that between plus or minus 2 standard deviations is always 95%. Okay. What percent took between 13 and 25 minutes? Here's 13, here's 25. I would add up 13.5 plus 34 plus 34. And I'm going to get 81.5% right there. Okay. One more question. What percent took longer than 17 minutes? Here's 17 minutes. What percent took longer? I add them all up. Or I can add up the percent that were below 17 minutes, because that's less numbers, and subtract them from 100. Either way, you're going to get 84%. So again, that one had 2 methods. Okay. This one says, what is the minimum time, or this should really say the maximum time, the top 16% got? Now, what's tricky with this is these are race times, right? So the top 16% had shorter times. So we're not going to look up here, even though we usually think of better scores being up here. These are times, so faster is better, and that'll be smaller times. So the top 16% of participants got, we want 16%, so that would be the 13.5 plus the 2.35 plus the 15. They got That's the top 16%. They have the shortest times, and they were at 17 minutes. Awesome. That is it for our video on empirical rule.